Our first speaker is Paolo Venneri. He is CEO and Director of USNC Space, and that is the space arm of Ultrasafe Nuclear Corporation. He has a PhD in nuclear and quantum engineering from the Korea Advanced Institute of Science and Technology. He has won an ARPA-E award and was among the first proponents of LEU fuel for space nuclear applications. Paolo.
Thanks.
It's not, why is it not showing? That's a good question. Let's see. Aspetta un attimo.
So I assume we want to do this in English, though, right?
Yeah.
Okay. Please.
Sorry, we're having technical difficulties with the projector.
So I guess kind of as background in terms of what kind of audience we have here.
Ah.
How many nuclear engineers do we have in the room? Okay, so a good amount. All right.
It's more than I thought.
Okay, came back. Okay.
Okay, so a couple things first that I need to clarify is that USNC Space or USNC Tech is a subsidiary, an independently operated subsidiary of Ultrasafe Nuclear Corporation. This is a clarification that needs to be made because, you know, ownership issues, interesting things. Now that I've got the kind of obligatory message out of the way, if we can go to the next slide, please. Now I just gotta scroll down. So USNC Tech has the honor essentially of holding what we believe to have some of the premier reactor designers for space nuclear systems in the United States. We have a group of about 9 people, most of us coming from the Center for Space Nuclear Research, which was directed at the time by Dr. Steve Howe, which is present outside, and then is currently run by Dr. Steve Herring. And while we were there, we were instrumental in developing the idea that a low enriched uranium fuel could actually enable an NTP system that had the same performance characteristics as an HEU system. While there, we worked with Dr. Mike Houts and pretty much a good chunk of the people down at Marshall Space Flight Center, and then eventually with the larger NTP program to really develop this concept and show that HEU is not a requirement to have a high performance NTP system. Since then, we've gone on to look at other concepts within NTP, looking at different fuel alternatives, different design concepts, and then also looking into fission power systems. Collectively, we've all produced something on the order of more than 60 space nuclear publications, and then we've developed a pretty extensive network of collaborators, both in the industry, academia, as well as government, to really push the design limits of low enriched uranium nuclear powered systems. Next slide. Kind of at the heart of what USNC Tech does on its own, outside of the government programs that we're supporting, is really developing a nuclear fuel that is, we think, ideal for both terrestrial applications and multiple space applications. This all has its roots, as most anything nuclear in the United States does, in one of the Department of Energy programs, this being the accident tolerant fuel program. The kind of key fuel IP that Ultrasafe Nuclear has, and then as a consequence, USNC Tech has, is called fully ceramic microencapsulated fuel. This is a concept where you take coated particles, coated fuel particles, and then you put them inside of a refractory carbide matrix. The result then is essentially an accident tolerant fuel, or a fuel that can operate at elevated temperatures and not have the loss of fission products. Now, in the words of one of my collaborators, this fuel here, because of its high temperature performance and because of its ability to retain fission products at elevated temperatures, we think it's essentially the ideal space reactor fuel. And so based on that, we've gone on to develop a whole host of different design concepts that kind of are enabled by this fuel in particular. Again, also building on both the experience that USNC is developing in commercializing this fuel and then resulting reactors on the ground, and then as well as the manufacturing experience and then developing of the fuel.
Excuse me.
Okay. Now, the rationale as to why USNC even had a space reactor arm and then eventually a subsidiary is the perspective and the idea that there will be a space economy. You have billionaires such as Elon Musk as well as Bezos really pushing for the idea that a space economy and a spacefaring species is the direction that we're going. Now, it's very hard to make a business case in the near term on plans that are going to come to fruition in a couple decades. So what we then went and did is we went and looked at kind of public literature and looked at the different mission concepts that have been published that would require a space nuclear system. And we put them roughly into 3 different categories. We have in-space power up in the red, we have nuclear electric propulsion in the purple, and then we have green being NTP. When we look at this, even just in the next 10, 15 years, we have a large number of missions that need nuclear powered systems in order to be viable. We go from 1 kilowatt power systems, where a year ago they were saying they would need in 2024, going up to 100 kilowatt scale, which is 1 medium power systems, up to megawatt scale power systems, already starting in 2027, if they really want to do what they're saying they're going to do. So next slide, please. So because of this, USNC Tech has been putting a not inconsiderable amount of internal development money and time into developing different types of nuclear powered systems for space. We've been doing work in surface fission power systems because that's what you need to do in the short term. But we've also been specifically looking at surface fission power systems, nuclear thermal propulsion systems, and nuclear electric power systems. All of these based around the fuel that we have within USNC and USNC Tech. Next slide. Now, because we're a commercial entity, starting from the idea that we have to be able to buy this fuel, have to have a reliable supply chain, we need to be able to work with it, we started with the idea of low enriched uranium fuel. We don't have the luxury of being large government contractors. We don't have the luxury of having had a large history of working with government programs, both on the weapons side as well as military systems. So our baseline assumption was we can work with low enriched uranium fuel. And so we applied, and so when you go about designing a low enriched uranium fuel system, you essentially follow very similar steps to what Dr. King was saying. You have to maximize your utilization of your uranium inside the reactor. This is done by increasing the moderation side of the core. You have to reduce your parasitic absorption, that is absorption of neutrons by non-uranium atoms. And then you also have to reduce your neutron leakage. And this is a combination of either reducing your surface to volume area ratio, as well as adding reflector sizing, or adding neutron reflectors. This allows you to really bring down and shrink down the size of your reactor when you've essentially removed fissile inventory from the core by going with a low enriched uranium system. Next slide. So the first of these systems that we really kind of started putting together is what we call the Pylon. And the idea behind this system is to really find what the minimum viable fission power system is that we can put together. It uses low enriched uranium fuel. It operates at conservative operating temperatures, so very similar to what Jimmo looked at back in the 90s. Uses existing and well-known materials, so we're not going for refractory cermets. We're going for stainless steels, Inconels. We're not going for exotic materials and not requiring a new materials development program. And we're also trying to maximize the use of off-the-shelf components. Again, really leveraging off of work that had been done back in the 90s under the Jimmo program. And we really designed this for near-term space applications. So trying to go with a single concept that can be scalable from tens of kilowatts up to a megawatt scale, and then can actually be applicable to near-term NASA missions as well as private missions, going from IRCU, electrical power, and then really demonstrate industrial processes on the moon. Next slide, please. And so when we go about doing these reactor design concepts, we came up with three baseline power levels that kind of to show initial feasibility. One being a 10 kilowatt, a 150 kilowatt, and then a 1 megawatt system. What we found was that these aren't crazy numbers. They're numbers that can actually be implemented in near-term missions. We have a turbine inlet temperature of 875 degrees Celsius, which is reasonable with current turbine technologies and materials. We're aiming for a 10-year lifetime, largely with the assumption that very few systems out there are designed for operating continuously for 10 years in remote locations. We use high assay LE of 19.75 enriched uranium, U-235. And then we use, again, this FCM fuel, so coated particles inside of a silicon carbide matrix. And we designed these systems also to be able to fit on a CLIPS class lunar lander. So to have a total system mass of less than 5 metric tons. So next slide. When we look at the mass distribution of these systems, they're actually not that bad. When you compare them to kilopower systems on the 1 and 10 kilowatt level, they're significantly more massive. But at the same time, the argument that we make here is that the very same technology that is used for these 10 kilowatt systems is the same reactor technology that you use for the 150 kilowatt system, and which is also the same reactor technology and materials that's used for the 1 megawatt system. So essentially, the trade-off we're doing here is sacrificing near-term high-performance systems for a long-term value out of the initial research and development. Now, this is all contingent that you can actually put on a CLIPS lunar lander a 2-ton metric system, and you're okay with having 3 metric tons of other payload for the rest of the stuff you want to put on the moon. If this trade-off is acceptable to the mission designers, then this is a perfectly valid mission architecture to propose also in the development of these systems down the road. Next slide, please. Now, one thing that we were very conscious of was trying to compare this with existing high enriched uranium systems. And so here you have a comparison of these Pylon systems compared with kilopower level systems and HU systems. And so the interesting thing that we find here is particularly when we start looking at the comparison between the 150 kilowatt Pylon system and the 200 kilowatt JIMO reactor. The JIMO reactor is, at this point, the state-of-the-art HEU system that was developed jointly by NASA, Department of Energy, and I think the Navy as well. And the masses of the JIMO reactor and the Pylon at the 150 kilowatt level are comparable. And so this goes to show that even with that essentially at 150 kilowatts, LU fission power systems using an accident-tolerant fuel that is based for coming out of the terrestrial program is comparable with an HEU system. Now, if the only power requirements you're going to have in space are 1 and 10 kilowatt systems, this is not what you want to do. But if you envision a future where we need 150 kilowatt, 1 megawatt, multi-megawatt systems that are based on terrestrial technology that are then applied to in-space applications, it's a good way to go. And it's one that is scalable much better, I believe, than the current architecture coming out of the kilopower program. Next slide. Now, because kilopower is the current baseline for many in-space applications, and there has been a lot of talk about trying to look at LU conversions of kilopower, we also looked at what it would take to have an LU kilopower system, much in the same way that Dr. King did with the student. And so one thing that really kind of comes to mind when I look at these different results is that LU kilopower systems are doable. Pretty much everybody who looks at these systems comes up with relatively similar results. And actually, the first LU kilopower systems that were looked at were not actually done in the United States. Those were done through a combination of South Korea as well as Japan, publishing in the early 2000s about what would it take to have an LU in-space fission power systems. And those results are very similar to results that we've come up with, and also very similar to results that LANL itself has come up with, in terms of really looking at what the different options are for kilopower system design. Next slide, please. And so when you really look at the different masses of these LU and HEU systems, we find that particularly if you go to a thermal spectrum or a zirconium hydride moderated kilopower system, the difference in mass between an HEU, full metal HEU system with a moderated LU system is not that bad. We have at most 100 kilograms increase in total system mass.
Is this 1 kilowatt or 10 kilowatts?
This is 1 kilowatt system. And so even at the 1 kilowatt size level, it is not, we believe, a performance game changer. Now, if you went with a solid metal LU system, your mass skyrockets and you get results similar to what Dr. King was quoting earlier. Now, one sec here. The key thing to kind of keep in mind here, however, is that the difference between a LU system that goes around the same kilopower system and the HU kilopower system is that the LU systems need zirconium hydride moderator. This is a development requirement for essentially any competitive LU system that basically relies on a kilopower system architecture. This is something that the current metal HU system from kilopower does not have. Okay, next slide, please. Now, the problem with coming after a whole panel already came before you is that you often repeat yourselves and kind of piggyback off of each other. And so this is essentially just reiterating what Dr. Shihai mentioned earlier, maybe phrased a little bit differently. But when we look about these systems, there's really 4 different things that, at least from a commercial side, we're looking at when trying to determine what pathway to take. One is that it has to meet the performance requirements. And this is, reliably provide power for the duration of the mission, as well as meet the mass and volume requirements of the system itself. This is kind of the baseline. If you don't meet these, you don't have a pull for your technology or your system. Something that has come up increasingly with increasing frequency is that the system you design also has to be manufacturable. The difference between a paper reactor and a real reactor is you can make a real reactor, and it works. But there's also an added dimension to this is that it can be made at the scales that you need. So instead of, if from a commercial standpoint, you don't just want to make 1 reactor, you want to be able to make tens or hundreds of them. And you have to have a method by which you can manufacture these. You also need a reliable supply chain. If, as a commercial entity, I had to buy HU fuel every time I wanted to put a space reactor into space, it would be problematic. Or there would have to be some kind of change in the regulations that would allow me to do that. And that would be some additional work on our part. It also needs to be affordable. And when I talk about affordable, there's 2 dimensions to it. One is monetary. Like, it can't cost $3 billion to make a 1 space reactor every time. There's also the affordability in terms of time. And that's something that's very hard to quantify because missions move, missions change. But at the end of the day, the system that we design needs to be able to be built within the time frame that's going to be eventually be needed. And finally, because we're a commercial entity, we have to be able to design a system that we can then eventually commercialize. The United States government is a wonderful customer, and we are always happy to work with them. And in fact, that's what we do right now. But eventually, we want to be able to go to a private market. And having a technology that we cannot commercialize to a private market makes it difficult for us, particularly moving on to next stages of development as a company itself. Next slide, please. So kind of some final technical thoughts for this discussion is, one, at about 100 kilowatts, the performance trade-off between HU and LU becomes a lot less clear. They become very comparable. This is particularly because above the 100 kilowatt level, your system mass begins to dominate your power conversion mass begins to dominate the mass of the entire system. And so you're much less sensitive to the mass of your reactor. And particularly if you're aiming just for 10 years of lifetime, above your reactor masses aren't going to change much aren't going to be very different between HU and LU systems at above 100 kilowatts. We've also started looking at these 10 kilowatt systems because we hear rumors that 10 kilowatts might be what NASA's going for. And we think if we stick with these kilopower architectures, we could actually get a system, a 10 kilowatt system that is actually very comparable in mass between an HU and an LU system. Now, one of the key reasons, as far as we've understood, as to why an HU system is desirable is because it is about as simple as it gets. You're able to have a fast spectrum reactor. And I know Bobby earlier mentioned that a paper reactor is an elegant, simple reactor. Kilopower is an elegant, simple reactor that you can build. So it's a paper reactor that is reality. And from my perspective, it's about as good as a reactor design can get. The problem is that it's not scalable, and it works for that 1 kilowatt, 10 kilowatts, 1 kilowatt, 10 kilowatt scale, and it's beautiful. If you go to an LU system, the simplicity of that system, particularly on the reactor side, is not going to be there. You're going to have moderators, you're going to have different temperature feedback mechanisms, you're going to have some hydride loss components that you need to take into account. It becomes a little bit more complicated. Not undoable, but you no longer have that beautiful simplicity of an HU fast spectrum kilopower system. Three more points. So commercial systems need to be commercially viable so that when I go to an investor and say, hey, I would like to make reactors for a large space market, an LU system, or it needs to be commercially viable. We see LU as being a key design decision from a commercial standpoint to be able to do that. When we look into this, reliability of the fuel supply chain is a key component. If we stick with high assay LU or even LU, we're able to rely on not only domestic supply chains, but also international supply chains in terms of supplying the uranium itself as well as the fuel. We're talking about European countries, Japan, South Korea, even South Africa for that matter. And then the key linchpin towards the implementation of a high performance LU system is development of zirconium hydride materials or high performance moderators. And this is something that we're doing both internally as well as in collaboration with the NTP program through NASA, and then informally also with different universities, because the development and manufacture of this high performance moderator is a really key development requirement for high performance LU systems. Now, one thing I need to emphasize, also particularly in light from questions during the previous panel, is that from our perspective, NASA has been supportive of development of LU systems and really looking at the technical feasibility of LU systems across the board. When they are sitting down and looking at HU versus LU, they really are making a comparison of what are the performance needs and whether we can meet them with an LU system. The LUNTP program happened because we showed that you could have comparable performance without sacrificing too much in terms of development needs. And so it's something that NASA is willing to do and has a demonstrated past of looking into.
Thank you.